A client initiates a payment request. The server processes the charge successfully, but the network connection drops before the success response reaches the client. The client, unaware of the successful transaction, automatically retries the request. Without proper safeguards, this results in two identical charges for the customer. This scenario is not rare. It is an inevitable consequence of distributed systems and unreliable networks. The financial and reputational damage from double charging necessitates a deterministic mechanism to ensure that executing the same operation multiple times yields the same result as executing it once. This mechanism is the idempotency key. We must treat every incoming request as potentially a retry, even if the client claims it is the first attempt. The core challenge is mapping a client's logical operation to a single, immutable state change on the server side, regardless of how many times the HTTP request is received. The idempotency key is a unique client-generated token that accompanies the request, typically placed in the HTTP header as idempotency key. This token must be a cryptographically strong, non-sequential identifier, such as a UUID version 4. The client is responsible for generating and reusing the exact same key for any subsequent retries of the same logical operation. The server uses this key as a lookup index to determine if the operation has already been processed or is currently in flight. If the key is missing, the server must reject the request with a 400 bad request, enforcing its mandatory use for state-changing operations like payments. The key's uniqueness guarantees that even if the client sends the request 10 times, the payment processor is only invoked once, based on the first successful key registration. Effective idempotency requires persistent storage. We need a dedicated database table or a highly available cache like Redis. The schema must include the idempotency key itself, the authenticated user identifier, the API endpoint path, the request parameters payload, the current status, and the final response payload. The idempotency key must be indexed, and critically, a unique constraint must be enforced across the combination of the key and the user identifier. This composite unique index prevents one user from accidentally or maliciously reusing a key generated by another user. Storing the full request parameters is essential for integrity checks later, ensuring that a client does not attempt to reuse a key for a different transaction amount or currency. When the server receives a request with a new idempotency key, the first step is an atomic insertion into the storage layer. This operation must be transactional. We attempt to insert the key along with a status of pending. If the insertion succeeds, the server proceeds to process the payment. If the insertion fails due to the unique constraint violation, it means a concurrent request with the same key is already being handled. This atomic operation is the foundation of preventing race conditions. In high concurrency environments, using a database transaction with a select for update lock or a distributed lock manager like redlock around the insertion attempt ensures that only one thread successfully claims the key and proceeds to the payment gateway. Upon successful atomic insertion of the pending key, the server executes the core business logic, such as calling the external payment processor. If the payment processor returns a success status, the server immediately updates the idempotency key record. The status field is changed from pending to completed, and the full response payload received from the payment gateway is stored in the response payload column. Finally, the server returns the successful response to the client. If the payment processor returns a definitive failure, the status is updated to failed and the failure response is stored. This ensures that subsequent retries will immediately retrieve the stored failure message without reattempting the charge.
If a request arrives with an existing idempotency key, the server checks the stored status. If the status is completed, the server bypasses all business logic and immediately returns the stored response payload using the original HTTP status code, typically 200 OK or 201 created. This is the core deduplication mechanism. If the status is pending, it indicates that the original request is still being processed. The server should return a 409 conflict status code, informing the client that the operation is currently in flight. Alternatively, the server can implement a short, bounded wait loop, polling the status, before returning the 409, allowing the client to potentially receive the final result if the original request finishes quickly. Many payment processors use asynchronous webhooks for final confirmation, meaning the initial API call returns a 202 accepted status before the charge is finalized. In this scenario, the idempotency key record is initially marked as processing. The webhook handler, when receiving the final confirmation from the payment processor, must retrieve the corresponding idempotency key record using the transaction identifier. The handler then updates the status to completed or failed and stores the final response payload. If a client retries while the status is processing, the server returns the 202 accepted status code, indicating that the operation is still pending final resolution via the asynchronous channel. Idempotency key records cannot persist indefinitely. They consume storage and slow down database lookups. A time to live, or TTL, must be defined. A standard TTL is between 24 hours and 7 days, covering the practical window for client retries. Implement a background garbage collection job that periodically deletes all Idempotency Key records older than the defined TTL. When a key expires, the server treats any new request using that key as a completely new operation. If the client attempts to reuse an expired key, the server will proceed with the atomic insertion attempt, potentially leading to a double charge if the original transaction was successful but the key record was deleted. To prevent a client from reusing a successful payment key for a different, cheaper transaction, the server must perform parameter integrity validation. Before returning a stored successful response, the server must compare the request parameters of the incoming request against the stored request parameters payload associated with the Idempotency key. If the amount, currency, or recipient identifier differs, the server must reject the request with a 400 bad request, even if the key is valid. This ensures that the key is bound not just to the user and endpoint, but also to the specific financial details of the original transaction, maintaining system integrity against replay attacks. Always use specific HTTP status codes to communicate the Idempotency state clearly. Use 200 OK or 201 created when successfully returning a stored completed response. Use 409 conflict when the operation is currently in flight and the client must wait or try later. Never use a 500 internal server error for Idempotency failures. These are client-side issues or expected concurrency scenarios. Ensure the stored response payload includes all necessary headers and body content, so the client receives an identical response to the original successful transaction. Finally, document the required key format and TTL policy clearly in your API specification, setting client expectations for retry behavior.